Okay. Think think that's a decent. I think can't remember exactly how many of you there are. Like roughly 40, I think. Yeah, yeah. All these are going to be recorded and posted, and eventually time stamped and all of that. So this will be, um, I thought, would be a lot more convenient. So yeah, I'll take a few minutes to mention why it is I'm doing this instead, because I was asked earlier in class why I was doing this instead of Zoom or something. Well, I've never really used Zoom. I'm having my TAs do it for large lecture discussions. I've never really used Zoom. I mean, I've never done any YouTube streaming either. But one thing is that using the YouTube streaming, I knew that I could just have everything recorded on like nice central account, and I could put timestamps on videos for like when I did certain examples and all that kind of thing. So that's I wanted to do that. And also Zoom has a problem where this semester one of my classes has almost 300 students in it, and I wouldn't be able to use Zoom for it. I think Zoom has a hard cap of like 100 students or something. Um, let's see. Grade weights. I think I already posted that in the Elms. Did I not already post that? In the Elms announcement. Let me see here. If I didn't post that already, um, then that was, huh? I didn't include it in the announcement, but I think I did in the. Oh no, I didn't. Okay, yeah. So basically, main thing to note is that going forward, the main the main thing that you're going to have as graded assignments are one more. So you already had your midterm that was take home, and it didn't have an in class part because I canceled that Thursday's class. So that's going to be your main. That's just going to be your entire midterm grade was the take home portion. Um, and which reminds me, um, actually, I'm just looking at this now. So uh, I'm trying to remember what I actually uh, said here for your class. Yeah, so the main graded components that remain then are so the main one is going to be a single final exam, which the format of that is I'm just going to post um, the final exam, and you're going to have like a few days, like 2 or 3 days to do it, and then you'll submit it via Elms or you'll email it to me, and it'll be graded um, like that. So yeah, that's the main assignment that is left. And then periodically I'll assign. You don't have to be like in lecture. I will make an announcement, so you don't have to like watch this as I'm live streaming these to get the assignment. So um, I will make announcements when I am going to assign like a couple of problems out of each of the sections when we do them, like I had been doing already. So a couple of those uh, will be assigned, I don't know, something like every maybe week and a half or something. You'll have an assignment. You'll have days, many days to do it, and it'll only be a couple of problems. And so you'll submit those either via Elms or I'll just have you all email it to me. Um, let's see here. Oh, yeah. So the pass grades. The thing is that a lot of these, first of all, some should have been posted by your grader because um, your grader actually had some of them on him when he couldn't go back to campus. So some of them Actually, none of them have been posted. Oh, oh, that's my fault for not creating those columns. So yeah, your grader actually has a lot of your uh, grades that he can input later when I add those columns. So that's my fault. I forgot to do that. So yeah, all that stuff's already been done. I just haven't actually put it up yet. So yeah, you'll. So hopefully over the weekend I'll have all those grades in. So most of the rest of them I already have in my grade book. I just haven't put them on Elms. Let's see. Did I answer everybody's question? Yeah, I already said that these are going to be recorded, so you don't have to actually be here. Yep, that's pretty much it. So what else do I want to say? Yeah, so the main thing, and again, I'm gonna make more announcements, and I'm gonna revise your syllabus into something approaching like the final form that it's gonna be in for the rest of the semester. But the point is, so sometimes I may record lectures and not stream and just post those recordings. So like this weekend, since we missed Tuesday's lecture, I may record something over the weekend and post it. But what I'm not gonna do is I'm not gonna record like a ton of lectures in a row and then like pile them on you at once and say, okay, now you have homework due, like the week after or something. I'm not gonna do that. So you all will not, I'll make sure that you all don't bear the burden of this stuff, so that it's, it will be as as easy as I can make it on you. I will try to lighten your load as much as possible. Anyway, what else? I think that's it. I think that's all I wanted to say. And like I said, if something doesn't work out, or if I think of something that I feel like would work out better. In fact, for this class, it might even make sense for me to post lectures in advance and then sit through our live streaming sessions. You kind of use them like problem sessions. So I may do that. I'm not entirely sure, but I may do that. It might make more sense for this class than actually two of my classes. I think that would make sense for. But anyway, so we'll see. We'll see how that goes. But anyway, I was gonna go over. We had mostly finished the chapter 7 stuff, which was the stuff with Markov chains, right before what was supposed to be your in-class midterm. So what I wanted to do then was do the next chapter, which is something that is led into directly from the Markov chain stuff. It's kind of like a quick application of Markov chains, and that's the Google PageRank. So this is chapter 8 in the note. Let me check. I'm pretty sure it's chapter 8. Yeah, it's chapter 8 in the notes. So you will have to remind me if I'm like, I'll try to keep an eye out on the stream to make sure that I'm not. The first time I did this, I was sliding the paper around a little bit, so sometimes it would go off camera. But anyway, so okay. Apparently, Google PageRank doesn't actually refer to the page, and Google PageRank refers to Larry Page, not the fact that it's ranking web pages, which is kind of it's a pretty funny coincidence. Anyway, so the idea with the PageRank algorithm is to rank pages based on some criteria. So you have you imagine that you have a list of, say, all the web pages in existence on the internet. And the idea is that you want to come up with some sensible ranking of them, right? Some sensible hierarchy that would essentially tell you something about, say, how many. So for some specific page, for instance, how many other pages are linking to that page. And so obviously the more of the pages linking to some pages indicates that that page is somehow better, more popular, whatever, however you want to describe it. Um, but then, there's a problem here where you can't just do something simple, like judging how many pages link to some page, because if you use something really, really simple like that, the issue is that, for instance, any web page I wanted to, if I wanted to make web page, I could create a bunch of like dummy, like sock puppet web pages that would link to my page, and then I've just made my page, a better web page according to that metric, because now it has a ton of new web pages that I've made that link specifically, to my page. But is it really a better web page based on that, right? It shouldn't be. So then I would have to take into account what the ranking is of those pages that are linking to my page. And of course, if I just made a bunch of new crappy web pages, then those aren't going to be very important by the same metric. So that's kind of the idea. But how do you go about doing this? So to cheat or to spoil the fun, I'll say that there's an obvious relationship between this setting that I've described and Markov chains. So here's the example. It's straight from the notes. So say that suppose the entire internet consists of 4 web pages. So we'll call them page 1, 2, 3, and 4. No reason to be too creative. Okay, so entire internet consists of 4 web pages, pages 1, 2, 3, and 4. Linked in the following way. So I am going to draw this in the obvious way, where if you have an arrow pointing from page to another page, it means that that page links to page in question. So let's say that I'm going to describe them up as page 3, page 4, page 1, and page 2 here. So page 1 links to page 3. It also links to page 2. And page 2 links to page 3. And page 4 links to page 3. But also page 3 links to page 4. Okay, did I get everything? And just making sure that I copied this diagram correctly. I think I did. Okay, so yeah, all those arrows are clear now. Okay. So notice, the second I draw a picture like this, then you know that what I'm drawing is at least superficially similar to a Markov chain. Every time we drew those Markov chain pictures, looks something like this. So then if this is going to be a Markov chain, then I should draw weights, right? I should list weights on each of these arrows. And so the point of a Markov chain is that the weights that I would list on some arrow are going to be probabilities that I'm assigning, right? So in the context of these web pages, what are the probabilities going to tell me? So the probabilities are going to tell me basically the probability that if I'm on some certain page, that I move to some page in question. So maybe I'll repeat that. So let's say, for instance, I am at page 1, right? So I am web surfer, and basically the idea of like a random variable, or being in a general position in this context, is I'm a random web surfer. So I'll mention that term again here in a little bit. So imagine I'm a random web surfer and I begin at some page. So Let's say I'm at page one. Well, page one has two outbound links. It links to page two and it links to page three. So the question is, if I'm going to think about this as a Markov chain situation, then how would I assign probabilities and what would the probabilities mean? So the a sensible probability I could come up with is like the probability that I browse right from one page to the other or one of the others. And so since this has two outbound links, maybe I should assign them equal weight, right? So I say it's equally likely that I choose one of those links over the other. Um, and so it's essentially that I'm choosing the links randomly, right? So I'm on page one, and then it's a completely equal probability that I go from page one to page two or from page one to page three. For instance, okay, so this is kind of the assumption that I'm making. Okay, so then what's a problem with this? So one problem is, you might say, this is clearly not really how people, well, I mean, maybe you browse the internet like this, but most people, I would say, don't really browse in this fashion where you just kind of randomly, I know that maybe what I'm saying is actually false, because if you've ever been on Wikipedia or a similar site, YouTube is another example, you might feel like you do sort of browse in a random fashion where you start somewhere and then you just kind of randomly click on suggested links until you end up God knows where. But for the most part, in the way that web traffic goes, it is not decided in this way. So if you're on some web page, you don't just end up in some random outbound link. There's something to the selection. So one problem is that it just doesn't really mesh with how web surfing behavior goes. And the other problem is that what if you have a page that doesn't have any outbound links, right? So in this diagram, what if these three arrows go into page three, but page three has no outbound link? So then in that instance, the problem of assigning probability, if you wind up at a page with no outbound links, that definitely seems a little strange. Now, one benefit of describing this as Markov chain, one benefit here is the following. I was just going to look at the comments for a second. What was it? Let's see. Yeah, we're doing something. So yeah, we're not gonna worry about a back button for now. So yeah, we're being like mega basic. Yeah, so the back button doesn't count as a link. How long will the videos usually be? Like roughly an hour-ish. This one will probably end up being an hour because I took a little bit of time talking about some transitionary stuff, but it won't typically like this lecture is definitely not gonna be a whole hour because the chapter 8 is pretty short. Um, yeah, okay, all right. So anyway, so the main thing then is we had an issue where this is one issue is that you could have a page that has no outbound links, in which case you might remember in the old case when we were just dealing with Markov chains, we could technically have that, but that meant something for the system that we were talking about, right? So you might recall there was some terminology and some stuff we talked about when we were dealing with Markov chains. So we talked about regular matrices or regular transition matrices, for instance, and what it meant for a problem. Um, so I'll get into that in a second. But like I said, another main problem is that it just doesn't. This kind of behavior just doesn't seem to model how someone actually browses the internet. But the benefit of this is that using that earlier Markov chain analysis that we did when we talked about looking at the transition matrix, and if the transition matrix was regular, we could talk about the steady state solution, or the steady state vector. And so we know that with Markov chains, the steady state vector was the vector that was tended to as your process continued indefinitely, right? So in the context of Markov chains, describing, say, population shift, right, or populations moving from some state to some other state, the steady state vector was basically telling you where people were most likely to end up, right? Where people were ending up at long-term behavior, or the end state, right? And so in this case, what would the steady state vector correspond to? Well, the nice thing about this is that if I interpret this as a Markov chain in some way, then the steady state vector is telling me what web page people would be most likely to end up at, right, eventually. And so just looking at this diagram, you can imagine if I could describe this as a Markov chain in some way, it seems like the page that people would most likely end up at is page 3, just because page 3 gets referenced by all the other pages, right? Or gets linked to by all the other pages. Okay. And so I want to come up with a nice interpretation of this that makes sense, and addresses those problems that I mentioned. And so the Google PageRank algorithm is something that exactly does that. So what is the approach? So the idea is I want to come up with a Markov chain description of the above picture, the above setting, that addresses the problems. So the two main problems are, one, what if a page has no outbound links? And two, what if a random web surfer behaves much differently? Which is really just to say that this, model is not a particularly good one, for modeling how people actually surf the internet. Okay. Note, I should say note. The steady state vector has a nice interpretation. So assuming that we can make it work out, the steady state vector has a nice interpretation, which is it's the page where a random web surfer would most likely end up. So it's the fact that this is the case means that's kind of the motivation for turning this into a problem involving Markov chains. Okay. All right. So anyway, okay. So how do we do this? So what is the actual Google PageRank algorithm? Okay. So here's the process, and then I'll return to this example and show you how this actually works. So here's the process. So one, assume a random web surfer, hereafter called RW. So a random web surfer starts at some page. Okay. So two, if the page has no outbound links. Maybe I should do let's do the case that has outbound links first. No reason to do the no case. If the page has outbound links, then there is an 85% chance that the random web surfer chooses one of those links. And we'll assign an equal probability in each case. So equally likely is each choice. It's kind of some Yoda speak. I'm speaking backwards there. Okay, so there's 85% chance that one of those outbound links is chosen, and I'm not going to say which is more likely. I'm just going to say all of those are equally likely. So that's 85% chance. So that leaves a 15% chance of something else occurring, and that something else is that a page is chosen at random from all possible pages. So there is a 15% chance that the random web surfer chooses a page at random from all possible pages. Okay, so just very quickly, what is it that's going on here? You're on page. If the page has outbound links, 85% chance you choose one of those links. It's completely random and equally likely which of those you pick. But there's a 15% chance that you don't choose any of those links. You just choose a random page from all possible pages. So maybe some of those pages that are included, you pick one of those, pick from one of those. That's an 85% chance of that occurring. But 15% chance you just pick a page at random from any possible page. Okay. All right. What is this doing? Going back to our picture, maybe let me grab this. So going back to our picture, in the way that we have drawn this, what is going on here? If I'm assuming that number 2 is how I'm going to structure things, then when I look at this picture, if I'm thinking of connections between pages, right, then I have to come up with, first of all, I have outbound links. That's like these hard arrows. But then if someone can go to from any of these pages to any other page, right? And we know how the internet works in terms of, I don't have to pass through some other page to get to another page. There's no there's no middleman. I can go from any page I want to any other page I want. And so technically all of the pages are connected in this way, right? So if I actually wanted to draw a diagram that illustrated what's going on here, if I assume that number 2 is true, then I would actually have to connect all the pages to every other page, right? But of course, I could do that in a small diagram like this, but in any kind of larger diagram, you can see that'd be very, very annoying. And so even if that's going to be the case going forward, I'm not actually going to do that. Okay, so that's one thing that's been changed here. The other thing is the thing that takes care of the no outbound links problem. So if the page has no outbound links, then there is a 100% chance that the random web surfer chooses a page at random from all possible pages. And then the fourth assumption, so that we actually get this process that we want to talk about the end behavior, the long-term behavior of this. So just like in our Markov chain problems, we assume that this continues indefinitely. We want to study the limit at infinity. So the random web surfer does this forever. So our W will continue to do this forever. Okay. All right. And that's the process. Okay. So going through this really quickly, you see that this is going to describe a situation that is a Markov chain. Okay. So, but again, the picture I drew earlier is not exactly how this works. Technically, there's like connections from every page to every other page, so that this all works out. But I'm not gonna draw that, right? I would have to draw in all of those connectors in that 15% case, and I didn't do that. Okay. All right. So, so that's the idea. Now, let us return to my example. I'll put it back for a second so you can remember what that picture looks like. Okay, so maybe I'll put that picture right here and I'll continue writing. Okay. All right, so that's what my picture looks like. This is describing these pages. So what is the idea here? A couple things. So continuing my example. One, there is a weight of 0.15 divided by 4. The 4 is the fact that there's 4 web pages, and the 0.15 is saying I'm in the 15% chance that I'm linking randomly to some web page. Okay. Connecting P sub I to P sub j for all I and j. Oop, I'm going off screen here. Okay, there. All right. So that's the first thing. Secondly, there is an additional weight of 0.85 times 1 over n connecting P sub I to P sub j, provided that P sub I links P sub j and that P sub I links to n pages total. Okay, so think for a second where this comes from in the PageRank algorithm, right? This is our 85% chance of the time. It's 85% of the time chance to choose one of the pages that is linked to the page that I'm currently on. Okay, so note the transition matrix. So the transition matrix for this Markov chain is, notice I'm calling it a transition matrix already, even though it's maybe not that clear from what I'm saying here that it actually is a transition matrix. Recall that there's some things that the matrix has to satisfy before I can call it a transition matrix, but I'm just going to go ahead and call it a transition matrix because it turns out that it is. Okay, so the transition matrix for this Markov chain is, here, let me, still want that showing. So how do I write this? So then this is just from these two descriptions, what is this? So this is 0.15 over 4 times a matrix of ones. It's a 4 by 4 matrix of ones plus 0.85 times a matrix, which is the first row is 0. The next row is 1/2, 0, 0, 0. The next row is 1/2, 1, 0, 1. And the last row is 0, 0, 1, 0. Okay. Now, before I actually write out the simplified form of this t, question is, what is going on here? So, looking at this, I have a situation where, yeah, this is why I wanted this to be shown here. So, I have a situation where, in this case, or in this part of my transition matrix T, I'm in the 15% chance that I'm randomly choosing a page. And it is completely random from among all pages. There's 4 total pages, and I'm weighting them equally. So that's why this is just a bunch of ones here. Okay. So the fact that there's 4 options means that I have this division by 4 here. Okay, so that's where this is coming from. So that's easy to see. All right, so the next thing, in the 85% of the time case when I'm on a page, I have to consider what page I'm linking to. Okay, so why is this first row all zeros here? Where did these entries come from? So looking at how this works, this is me connecting pages to other pages. And you note that in this picture, page 1 has no incoming links, right? Has no incoming links. So what is going on here is that there's no page that links to page 1. Okay. What about page 2? Well, there's exactly one page that links to page 2. How do I determine this additional weight in the first place? So there's an additional weight of 0.85 times 1 over n connecting p sub I to p sub j, provided that p sub I links p sub j and that p sub I links to n pages total. So in this case, this would be p sub 2, or p sub 1 linking to p sub 2, and then it would be p sub 1 linking to 2 pages total. And it does. P sub 1 links to 2 pages total. Page 2 and page 3. Okay. And so this entry is a 1/2 here. Okay, because of it linking to 2 pages. Okay. Notice that this entry, I have, this is page, this would be, so I'm in the 3rd row, 1st column. So in this case, I have page 3 is linking to, so page 3 is getting linked to by page 1. Page 1 links to 2 pages total. Page 3 is also getting linked to by page 2, which links to 1 page. It's just page 3. Page 3 is getting linked to by page 4. And page 4 also links to a single page, so that's the reason for the entries 1 and 1 here. Okay, and then lastly, Nothing is, so the only thing linking to page 4 is page 3, which links to a single page, which is why there's this 1 here. Okay, so that's, I know that this is a little bit confusing to go through, so, you know, this would be a good time when you're working this out on your own to pause and rewatch the video for that description um, there. So basically, you can determine these entries by considering a page linking to that page and how many pages total it links to. So for instance, again, just to show you how this works, we'll use the third row as probably the best one to see. So page 3 gets, because we're in the third row, we're considering pages linking to page 3. So page 3 gets linked to by page 1. Okay. And it gets linked to by page 1, and page 1 links to 2 different pages. So that's why we have a 1/2 here. That's why the denominator is 2. Page 3 gets linked to by page 2, and page 2 links to a single page. So page 3 is the only page it links to. That's why there's a 1 here. Page 3 doesn't link to itself, so there's a 0 in this entry. And then page 3 gets linked to by page 4, so we're in the 4th column. Page 4 links to page 3, but that's the only page it links to. So again, there's a 1 here. Okay. Similarly, in the 4th row, there's a single page that links to page 4. That's page 3, and it links to only page 4. Okay, so that entry is a 1. Okay. Now I'm going to write. Now that you've seen that, I'm going to write out simplified form of this matrix. Actually, I'm not even going to bother writing that out. So it equals something. Okay, you can see this. This is on page 5 of chapter 8. Okay, so it equals something nice. And if you actually go through and look that to verify that it's a transition matrix, it turns out that it is. Okay, so it is a transition matrix. It turns out that it has eigenvalue 1, which means we can talk about the steady state vector. So steady state vector is the following. So I'm going to go ahead and just write out what it is. This is found in the exact same way the steady state vector is found for generic Markov chains. 0534, 0.4711, and 0.4379. Okay. Oh, so, well, I should say that in this example, we're assuming that, but in some of the, I think in one of the exercises this has changed, but the point is that I could change this up in such a way. I'm replying to the question of whether or not we can always assume the diagonal zeros. So maybe we talk about what it means for a page to link to itself. In this particular case, yes, that is exactly what that's telling you, but I could give you an example of something where you have pages linking to themselves in some way and trying to make sense of that. Okay, so yeah, that's definitely I could give you a question about that and how you would handle doing that or dealing with that. Okay, so then steady state vector is this thing. This is called the ranking vector. Okay, and what is this telling you? So what this tells you literally in words is P sub 1 has page rank 0.0375. P sub 2 has page rank, I'm not going to write all these out. Okay. All right, so this steady state vector contains these entries. These entries are the page ranks of the corresponding pages. Okay. So what do these things actually tell you? So let's do some analysis on this. So analysis of PageRank. Okay, so first of all, So piece of 3 is important because lots of pages link to it. Maybe I'll bring back the page ranks here. Okay, so looking at this, the highest page rank is page 3. We should have expected that. If you remember in the picture, every other page was linking to page 3. But notice that page 4 has a page rank that's comparable, right? It's like not that far off. Okay. So what does that mean? Well, the reason for that is that, remember, page 4 only had a single page linking to it, but the single page linking to it was page 3, and that was the only page that page 3 linked to. So page 4 is important by virtue of page 3 being important. So page 3 only linked to page 4. That was the only link that page 4 got. It was the only thing it was linked to. But page 3 being important gave importance to page 4 because of that. So page 4, so piece of 4, only has piece of 3 linking to it. But since piece of 3 is important, this is a 4. Piece of 4 is important. Okay. Not as much as page 3, which had literally every other page linking to it, but still, you know, it's comparable. Okay. Piece of 1 is the least important. And 4, which, oh, I'm off the page now. Okay, so piece of 1 is the least important. And the fourth takeaway is piece of 2 is only slightly more important than piece of 1, since piece of 1 is the only page linking to it, and piece of 1 is not important. So this is interesting because you could imagine a situation where you had a page that had a bunch of links, but because all of the links it had were pages that had like no links, that having a bunch of links from pages with no links was only worth marginally more than having no links at all, right? So in this case, piece of 1 and piece of 2 are actually, again, comparable, even though piece of 1 is not linked to at all, and piece of 2 has one link, but its only link is from piece of 1, which is, you know, not important. Okay. So I might do one more example of this stuff at the beginning of the next lecture I do, or in fact I may, like I said, I may record a lecture over the weekend and post it, or maybe not a full lecture, just maybe like a couple of me working through a couple of problems. And then we'll basically be done with this, because once you see how this works, then really what's most interesting about these problems has to do with the analysis of the situation rather than doing them, because doing these work out in the exact same way as the Markov chain problems. What I'll do is I'm gonna hang out here for like another couple of minutes before I end the stream in case anybody has questions, and then I'll end the stream, and this will be uploaded to this channel within a couple of hours, so that you can go back and watch it whenever you want to. And like I said, when I get some time, I'm gonna go back and add some timestamps. I don't think it's that important in this lecture, but in future lectures, it could make things nice to add some timestamps. But anyway, yeah, so I'm going to hang out for a bit, and then if nobody has any questions, I'll end the stream in like another couple of minutes.